results and magnetic fields in two kinds of galaxies, and I will show the magnetic field structures and the connections with other processes. First, I would like to show you the disturbed magnetic field in a specific Virgo cluster, spiral. Then I will introduce the idea of magnetic maps and discuss correlations between magnetic field components, which I mean regular, random, and total magnetic field strength, and the local star formation rate. I will also show you that an analysis of magnetic field's components could be of much help in recognizing if the dynamo-generated magnetic field in this galaxy is modified by ramp pressure or tether forces. Then I will report the recent discovery of magnetic fields in an early time galaxy of ringed morphology. I will show you the observed structure of magnetic fields in the galaxy's inner ring, and argue for a pure dynamo in this case, which develops without support from spiral density waves or any external forces. So the first galaxy to show is Virgo cluster spiral NGC 4254. In all the observed wavelengths, it is weakly disturbed. The spiral structure is dominated by one heavy, strong southern arm. There are also two other arms and some flocculent armlets in the northeast part of the galaxy. Our map of total radial emission shown here in contours also showed this disturbed spiral pattern. The magnetic field vectors always keep the orientation of the nearby density wave. So you can see that the pitch angle of magnetic vectors changes over the galaxy and is nearly zero in the south and more than 40 degrees in the north. But in all regions, the magnetic field tries to adapt to the local density wave. And the stronger irregular field is in the south and makes a kind of magnetic arm. We know that such magnetic arms exist in other galaxies, but usually they are shifted to the inner side of density wave, like, for example, also here in the north. But in this region, magnetic fields are shifted outside of the density wave, so to the downstream of density wave. Such untypical behavior can indicate that probably this magnetic field is modified by some external process. The disturbed magnetic fields are best visible in this very asymmetric distribution of the polarized intensity, where a strong polarized ridge is visible in the south, together with azimuthal, almost azimuthal magnetic field. What could be the cause for this global asymmetry? Maybe it is the ramp pressure of the cluster gas exerted on the galaxy during its passage through the cluster medium. This could compress magnetic field from this direction and produce anisotropic magnetic fields. We know that such fields give rise to the polarized emission, which is in fact observed here. However, this galaxy is far away from the cluster core, and it's not H1 deficient. So if there are some ramp pressure effects in this galaxy, they must be very weak indeed. Another possibility is provided by recent observations of neutral gas by Minchin and al. And they detected a range of H1 blobs along a bridge of or a tail, And if you look at the velocity space, they are connected with the southern part of the galactic disk. So maybe the distorted spiral is because of tidal interaction of this galaxy with another Virgo cluster member. These, again, the same forces could stretch and share magnetic field along the southern spiral arm and produce, again, an anisotropy magnetic field like in the case of compression. So we have two hypotheses for this modification of the dynamo field, ground pressure and tidal interaction. It seems that regular field, random field, and anisotropy field are very important to understand the evolution of magnetic fields in this galaxy. So to study these components of magnetic fields in detail, I brought here magnetic maps which present in colors here total, regular, and random magnetic field strength over the galaxy. They give the intrinsic values of the magnetic field strength free of projection effects and Faraday effects in the plane of the galaxy. They use the total power emission, polarized emission, polarization angle in each point of the map, and the equipartition assumption. So as you can see, the total field reaches about 25 microgauss, which is quite a large value as compared to other galaxies. The random field very well corresponds with the distribution of the infrared emission given here in colors. The regular field is also strong. It is up to 14 microgauss. But the regular field is not only strong in the southern polarized reach, which is expected, but also here in the interarm space in the west. This regular field was partly hidden in the polarized emission due to projection effects. So with magnetic maps, you can reveal some structures which you can easily miss due to some simple projection effects. These fields are best visible, in fact, in this map, which is the field regularity, so it's the ratio of regular to random field, so it's over here. I tried to analytically model the effect of compression and stretching on different magnetic field components. So taking into account the geometry of the reach and the direction of the possible active forces due to compression and stretching, and following famous papers, Sokolov and Begador, where they presented some idea how to scale different magnetic field components due to compression and stretching. I derived the degree of polarization in the polarized reach and the synchrotron intensity ratio in the reach and outside of it for the compression and the stretching processes. Without going much into the details here, when these values are compared with observations, it seems that compression enhances random magnetic field too much, but stretching well corresponds with the observational data. So I think that the tidal interaction is a proper cause for this modified magnetic field in the southern part of the galaxy. So discussing, analyzing magnetic field components give you a sensitive tool to reveal some physical processes as these acting in Virgo cluster spirals. What else can we learn from magnetic maps? They give possibility to analyze in details, quantitatively, the association of magnetic fields with star formation rate across the galaxy. In this first picture, I plot the total magnetic field strength against the star formation rate estimated from the infrared emission from the Spitzer satellite. As you can see, there's a nice correlation. It is not unexpected because this gives you in another representation the well-known radio-infrared relation. It also only tells you that even in disturbed spiral with high star formation rate, which is observed here in this galaxy, this relation still is present. But the second picture is even more interesting. It gives the field regularity, which is defined as the ratio of the regular to random field. In contrast to the total field, the field regularity strongly drops off when you go to the regions of higher star formation.
This is for a sample of galaxy?
This is for one galaxy.
One galaxy.
Yes.
And how do you estimate the star formation?
This is from, as I said, from infrared emission, from the map of infrared emission, and I use calibrators, new calibrators which were published by the team of Chemical and Calzetti in 2007. So, as you can see, in contrast to the total field, the regularity is smaller for higher star formation. What could be the cause for that? I also plot here the random field strength and regular field strength separately. For the random field, you see very tight correlation with star formation rate. But for regular field, there is no such kind of correlation. It is surprising for the regular field why it behaves completely different way than other magnetic field components. I think it's something very interesting and very important in these old pictures, which gives us some information about the dynamo process and turbulence across the galaxy. So what could be the cause for this anti-correlation of regularity with star formation rate? Probably there would be few possibilities. First, tangling of regular field in regions of enhanced star formation. Then production of turbulent field proportional to star formation rate, or production of regular field anti-proportional to star formation rate. And I found in the literature that there are some discussion about how this effect could be made. But because you can see very tight relation of the random field with star formation rate, I guess that the efficient production of turbulent field proportional to star formation rate is a principal cause for this anti-correlation. But of course, magnetic MHD simulations are needed, first of all, to probably say the same if the second possibility is valid, and also to explain in quantitative way all these relations which are purely observational results. Okay, so the second galaxy I would like to show is an early type galaxy of ringed morphology. Such ringed galaxies are formed by resonant accumulation of gas in non-axisymmetric gravitational potential. In this case, by an oval. It causes outer and inner Lindblad resonances to produce two rings. The outer ring is very weak and of the scale of this emission, but the inner ring is a very well zone of intense star formation. This galaxy have only flocculent spiral pattern, and in fact in many wavelengths the morphology is dominated by the inner ring. There are mainly circular gas motions in this galaxy with velocity about 200 km/s. Can we expect the generation of magnetic field in this situation? What kind of magnetic field structure can you guess? Well, this is a map of total radio emission in contours, and again it gives you the ring, the morphology of the ring. So radio features are well corresponding with the enhancement in the infrared emission, which is shown in colors. So both distributions must arise with the same intense star formation process. Radio contours in the galaxy bulge are slightly elongated in the direction of the nuclear minibar, which is best visible in CO images, for example. So all these things suits very well, I think, altogether. But the polarized emission and magnetic fields give completely different pattern. As you can see, magnetic field vectors are organized into a very distinct spiral pattern. So you can also see that the inner ring, plotted as H-alpha image, does not influence the magnetic vectors at all. They cross the ring without changes of their orientation. So, because here we do not see spiral density waves, we can guess that this spiral magnetic field must be of pure dynamo origin.
Chris, sorry, but your beam size is comparable to the width of this ring, right?
Well, yes, this is about 200 parsec. The ring, I think, is a bit like that, but comparable. So, to study a little bit more in details this structure without some projection effects, we made this phase diagram which gives you magnetic fields in the frame of the galaxy, free of projection effects in the azimuthal angle and logarithmic radial distance. So, and the spiral feature in this frame should be a straight line inclined by the pitch angle. As you can see, magnetic fields make a very coherent structure and are inclined to the ring plotted here with H-alpha image with pitch angle which is quite high, 35 degrees. There are some regions with smaller pitch angles on the opposite side of the galaxy, and I think they are corresponding with the nuclear minibar. Otherwise, the structure is very distinct. In fact, it is one of the most coherent magnetic spiral structure ever observed to date. When magnetic maps are produced also for this galaxy, you can see that magnetic fields are very strong, up to 30 microgauss in the ring and 14 microgauss in the regular field. They are strong when compared to typical spirals and are very strong when you compare to another early type galaxy, as Sombrero galaxy, for which Marita Krauss found 4 times weaker magnetic fields. So the dynamo process generating regular and random field in this galaxy must be very efficient. The last problem I would like to address is the high pitch angle of the magnetic field. Because it cannot be maintained by spiral arms, it could be probably due to configuration of the dynamo. So, according to Detlef Elsner, in alpha omega dynamo, the pitch angle is proportional to radius of the turnover in the rotation curve, the rotational velocity, the turbulent diffusion, and the width of the disk, the high scale. So if you take with the rotation curve some observational parameters and typical values for spirals, for eta and disk height, then you will get 2 degrees, much less than observed. Much less than observed. So either the disk is thinner, which is rather improbable, or the turbulent diffusion is much larger. So the turbulent in the ring must be larger than normally and maintained by, I don't know, maybe parking instability or magnetoroputational instability. So this is to be determined. What is the cause for this enhanced turbulence? Why the magnetic fields is crossing the ring, and why magnetic fields are so strong in this early type galaxy? Okay, so my birds from the first slide reached their destination. Is a high time for a summary. So in the case of Virgo cluster spiral, we found the disturbed magnetic fields which match the density wave. We found with help of magnetic maps that total random fields correlate very well with star formation rate, but the field regularity anti-correlates, and that the regular field does not depend on star formation at all, or almost. And some analysis of magnetic field components can discriminate between the tidal and drum pressure effects in cluster spirals. In the case of the ring galaxy, we have seen the radio emission which is associated with the inner ring, but the regular magnetic field ignores the galaxy's ring morphology and makes a spiral structure. Magnetic vectors cross the ring at large pitch angle, and the fields are very strong in this early type galaxy. If it is challenged or not for the dynamo, I don't know. This question for you. Thank you.
Thank you very much. Chris, with this estimate of the pitch angle which you just showed in the previous slide, I'm a bit surprised. Somehow the formula I'm used to use, the estimate from asymptotic solutions for disk diameters, gives you that pitch angle is just L over H, where L is the turbulent scale and H the scale height, which immediately gives you 1/4, 1/2 instead of 2 degrees. So where from that formula comes?
Even worse.
Where from that formula comes on the white background? What's the origin of this formula?
This is from this paper.
No, but physically, where from this formula comes?
Oh, this is just...
What are the physical assumptions?
This is alpha omega dynamo, which is quenching, as I remember, and this is just for analyzing the dynamo numbers.
Was it tested on other galaxies? Does it work
Yes,
for any
yes,
galaxies?
yes. That was tested for flocculent galaxies, and that was
Does it work
shown
for
that...
the Milky Way?
I don't know.
For M31, for M51, for normal, not flocculent.
Okay, you can check.
It's the same reason why I have this discrepancy in my pitch angle. So I use the same formula.
I suggest you use different formula.
But you will get, okay, the problem is if you will get
if the formula is just using the same formula to choose, I can tell you which
one. You will get larger pitch angle or not?
Yes. 35 degrees, 25 degrees, 1/4, 1/2 of radian.
So.
And for example, the picture which Rainer showed with pitch angles a function of radius from our rating of 1996 is fit by that formula perfectly well. Both the radial trend and the opposite values.
I'm happy with one problem.
So I'm surprised that there's a problem in this place which is
Okay, but
It's also a surprise for me.
then don't use this formula
but
if it doesn't work.
they are
But you see,
okay.
Potsdam people are not stupid.
No, if you come from a linear model, this means that non-linear model isn't good enough. And that's it.
But in that case, you of course must check. But in that case, you will also solve one of the Reiner's problems from this.
This was my
because
remark.
This is why I was
because this is connected with the Flockwork galaxies, for which we observe spiral features with large feature areas.
Then I'm pleased that at this conference we have solved at least one mystery.
My suggestion, I understand that it is a very important point, but maybe it is better to discuss it in discussion. Please, Natalia.
My question is, what's the level of equipartition fields for this galaxy?
Yeah. This is equipartition fields. So total magnetic field
No, not
strength.
total. According to the dynamic estimations of X-rays, all this stuff normally. According to kinetic energy, what's the level?
Probably in the outer parts of the ring, I can guess that is more than the kinetic energy of the gas. So like
You mean that magnetic energy larger, of regular magnetic field?
regular is 2 times smaller, maybe
Of the same level?
equipartition or something like that.
So you claim that you've got equipartition for large scale and over equipartition for small scale. Let's see.
Last question, please. No.
Yes. First, can you show again these very interesting results about the dependence of the turbulent field, or random field, on staff formation rate? What's the range in turbulent field? How much it changes? By factor of what? I forgot to know this.
Oh, sorry.
Just say number. What's the theoretical range?
Yes, come back, please come back.
Factor of 2, right? Factor of 2.
Yeah.
So, very interesting.
So thank you again. Next speaker is Brian Gensler.
2 orders of magnitude.
I've changed the title of my talk. I'm going to be presenting 2 different sets of work, one on turbulence and one on dynamos, that 2 of my PhD students have been doing over the last year or so. So most of what I'm going to be presenting is on behalf of my students who couldn't be here, Catherine Newton-McGee from the University of Sydney and Anne Mao from Harvard University. Those of you who went to the PAM meeting a couple of years ago met both of them. Plus a bunch of other collaborators, mainly in Australia, including Mareka Haverkorn, who's here, and various other people. So I'm going to talk about something which I know is dear to the hearts of at least some of you in the audience, and that's this topic which has been debated at length over the last few years, polarization canals. And what I mean by this are structures that are seen in maps of radio polarization, channels or little worms or whatever you want to call them, where when you look at the polarized sky, you see these narrow regions where there is not much polarization. So here's an example of this. This is a swathe of the galactic plane as mapped by Effelsberg. There are supernova remnants and H2 regions and background galaxies. So this is what you see in Stokes Eye. But when you look at polarized intensity, not only do you see a very different picture where not much correlation with total intensity, you very strikingly see everywhere these narrow worm-like structures, canals. And these have been identified in various maps for a while. Mareka Haverkorn has done most of the observational work on these. So some of the characteristics of these, well, they're seen both with single dish maps. This is single dish data and they're clearly visible. And they're also seen in interferometer data. So they're not an artifact of a particular type of observing or something missing about the signal recorded from the sky. They're inevitably 1 resolution element wide. So you can see the finite width of these, and that corresponds, as you can see from this compact source, to the resolution of the data. If I just jump back, you can see they're not related to anything in total intensity. They don't have any obvious structures in radio emission or any other wavelength that they correspond to. And Moreika and others have shown pretty convincingly that one of the things that these canals are inevitably characterized by is that from one side of the canal to the other, the position angle of polarization always jumps by 90 degrees. So with these characteristics in mind, what are canals? Well, there's various ideas that have been put forward. Haverkorn and Heitsch and other papers by Haverkorn have argued that canals are due to beam depolarization. That is that there is a small region where the angles change abruptly, and so when you average that over the resolution element, you get cancellation. And they argue that this beam depolarization is due to a rotation measure gradient across the sky. If you have a rotation measure gradient, then there's going to be particular values of the gradient that at a given observing frequency will correspond to 90-degree shift, and that will produce a contour lines corresponding to that particular gradient rotation measure. Shukarov and Berkhuizen argued that canals were contour lines, but not so much a rotation measure gradient, but contour lines of depth depolarization. That if you have a mixed blob of both emitting and rotating material, then there'll be certain points in that blob where all the emission from different parts of the blob cancels out, and the contours will trace constant amounts of depth depolarization at a given frequency. More recently, Fletcher and Shukarov have suggested that there could actually be a second type of canal, which are actually not due to Faraday rotation, but due to an actual physical discontinuity in angle. If you imagine a shock propagating through the interstellar medium, at the point where the shock is, there's strong compression and all the angles could potentially jump. And so you might actually be seeing some distribution of shocks from old supernova remnants spread throughout the interstellar medium. So, one way of understanding canals, which was really started by Fletcher and Shukarov, that we found very illuminating, is to look at how a canal behaves in the QU plane. That is, you have a canal in the sky, and you move spatially in X and Y across the canal, but you look at where the position of the emission in the QU plane goes to as you move across that canal. And so what I'm going to show you are data taken by Catherine Newton-McGee with the Australia Telescope Compact Array at 1.4 gigahertz. We've essentially just picked a random part of the galactic plane, chosen to be a region of strong diffuse polarized intensity from the interstellar medium. So, first point to note, and this is sort of an obvious statement, is that if you have some track, a winding track in the QU plane tracing the polarized structure as a function of position on the sky, then when that track passes through onto a canal, since the canal has zero emission in it, that has to be a point where the track passes through the origin on the QU plane. What's more, if you draw a line that passes through the origin in the QU plane, then clearly the angle must change and the QU plane must swing through 180 degrees as it passes through that point. So since the angle of the Stokes vector is double the true angle, you get a 90-degree shift. So any track that passes through the origin of the QU plane will naturally produce a 90-degree jump in angle as you require from the canal. So let's show you an example. This is just a small region, just a few arc minutes across. Black is high polarized intensity and white is low polarized intensity. And so you can see this heart-shaped region of polarization with these canals surrounding it on all sides, plus other canals over here. And so what we're going to be looking at here is three adjacent tracks going from high polarized intensity through the canal and out to high polarized intensity on the other side. So if you just plotted polarized intensity versus position, it would be high and then it would drop down and then it would go up again. But here's a plot in the QU plane. So here is Q, and here is U, and here is the origin. You start over here at A, all 3 points lie over here, and then as you move from A to B, the tracks pass through the origin as required, and then move out the other side to B. So if you plot angle versus position, then here you are at A, you have one angle, the angle is almost constant as you move in, and then very quickly as you get to the origin, the angle actually suddenly flips the other side, you have a 90-degree jump, and then it comes out the other side. So that's not very hard to understand, I hope, and this is something that Fletcher and Shukarov pointed out in a couple of papers a couple of years ago. However, what happens if you don't have what we might call a true canal, or what you might call a near-miss canal? That is, where the track doesn't quite pass through the origin. So an easy way to generate this scenario is if you take this track and you simply just apply a positive U offset. So physically, you could imagine that you see the structure, but then there's some other cloud in front of it that has nothing to do with it that emits in pure U. So all the signals will just be shifted upwards by some amount. So what will happen now is the angle will still change as you approach here and then ground here, but you don't get anywhere where you have a perfect canal because the intensity never goes to zero. And what's more, the angle doesn't change abruptly, it changes more smoothly, and it doesn't change by 90 degrees. So a near-miss canal doesn't have the same properties, but it certainly still has a swing in angle localized over a very short region. So you can ask yourself, these canals that people have been studying, are these just a special subset of a more generalized set of phenomena where the angle changes quite abruptly as it goes near the origin? And so you can say, well, is there any way we can, instead of making a plot of q squared of q squared plus u squared, where the canals reveal themselves as places where the intensity is low, is there a way we can make a different sort of plot to show places where you almost have a canal? And so a simple way to do that, which Catherine suggested, is to make a plot of what she calls shallow canals, where instead of plotting the polarized intensity at each pixel, you simply plot the angle, the dispersion and angle in a small box around each pixel. So obviously at a canal pixel right here, you have a large dispersion angle because it changes from this angle to that angle. And so canals will show up as regions where the dispersion angle is very high. But this near-miss region here will show up as a place where dispersion is high, but not as high as this one. So if you take this approach, you should get a map not just of the canals, but of all the near-miss canals as well. So here is a map of the whole region that we studied. So here is that little heart shape, and here's that canal we were just talking about. You can see other canals all over the place. So here is a map of the polarized intensity, but we're now going to switch to a map of angle dispersion. And I find this image quite remarkable. All the canals still show up quite nicely. So here is that heart-shaped canal right here. But you can see that there are fainter and fainter and fainter canals going off and off to infinity. This to me looks like when we all used to use transparencies, if you stack your transparencies on top of each other, you could very faintly see the writing on the bottom transparency, even though you're looking at the top one. But the further you go down into your stack, the harder it is to see. So what this tells me is that interstellar medium is actually full of canals, like a can full of worms. But this weighting shows them fainter and fainter and fainter the further they are from the origin. So you can clearly see that there are indeed these narrow winding structures that have all the properties of canals. They're one beam wide, they're long and wriggly, but they don't pass through the origin, they miss it. So what we've called canals are actually just a subset of something far more general. So we can ask us, and I should say the image on this doesn't really do justice to it. The image I have on my computer shows it in much more detail, so come and have a look afterwards. So what can we... There must be some more fundamental definition of a canal than simply a place where the polarization goes to zero. And you can get at this by looking at the QU plane and invoking requirements that there must be certain properties of canals that must be invariant under various transforms. So the most trivial one to understand is that canals must be invariant under rotation in the QU plane. So here is just a trivial example of rotational invariance. Here's a track in the QU plane that goes through the origin, so that you must get a canal at this point. If you rotate this track by any arbitrary angle, clockwise or anti-clockwise, nothing changes. All canals are rotationally invariant. This was a point made by Fletcher and Shukarov, who exploited this to make some certain statements about canals. And so some reasons why you might experience rotation of a canal is simply Faraday rotation. If you put a Faraday screen in front of your source, it will just pick up all the points on the QU plane and rotate them. Or simply a changing coordinate system. If we redefine where north and east are, then we'll have different definitions of Q and U. So a trivial example is that the canals must be invariant under rotation. What's much more interesting is translational invariance. It turns out that you can argue that canals are invariant under translation as well. So here is an example of a canal, a track that just goes from here to here, and it goes through the origin. So, as I showed you in an earlier example, what happens if we now simply look at this canal, but there is some other completely unrelated blob in front of it that emits in a constant offset in Q and U? So this canal will now sit over here because a constant Q and U are being added to it. Is this still a canal? Well, not by any formal definition, and it doesn't go through the origin, but nothing has changed. The properties of the interstellar medium at that particular location are unchanged. It's just that we're experiencing a foreground screen. Oh. That was my shoe that you were hearing. And some physical examples as to why you might get translational invariance. We could have a foreground screen. If the medium is, if you don't have any depolarization horizon, then it could just as easily be a background screen, so something behind it could also produce an offset. Or there could be instrumental reasons. If you're observing with an interferometer or under many conditions with a single dish, then you are missing the absolute offset, and that could also arbitrarily shift the canal to anywhere, shift the track to somewhere else in the QU plane. So unless you know that you have no foreground or background screens, and unless you have absolutely calibrated data, there is nothing intrinsic about a track that goes through the origin. The track could go anywhere else, and it's just been shifted to the origin by these various offsets. So if you ask, what are the defining intrinsic properties of a canal, I think saying that it has to go to the origin is not correct, because translational invariance tells you that any track could potentially go through the origin if the conditions are right. It turns out that it's got nothing to do with the location of the track at all, but it's actually the spacing of the points along the track. If you like, the velocity at which one travels along this track as one traces a line across your image. So the spacing of these points is basically set by the resolution of your image. If you have a coarse resolution image, then that means that the spacing of these points is quite widely separated. And you can see these points here, provided the translation is such that they go to the origin, will produce a canal because you have one point which is here. When you move to the next resolution element, you have flipped by 90 degrees and you have a canal. However, if you observe this same situation at very high angular resolution, you can now see that as you pass to the origin now, you actually have a small amplitude polarization, but you do not have a flip in angle over one single beam. So you can think of this as a low velocity track, and this could never form a canal no matter where you put it, where this one here is always going to be a canal provided it passes through the origin. So to answer the question, what is the actual physically intrinsic properties of a canal? It appears to be, if you invoke both rotational and translational invariance, a canal is somewhere where there is a very high gradient in the Stokes vector. That is where Q plus RU is changing very rapidly. And if you then shift that track to where it goes to the origin, you get a canal. So I would argue that a canal is simply a contour tracing a certain level of gradient in the Stokes vector. So how can we quantify that? So it turns out that there's actually a lot of similarity with issues in quantum mechanics here. That the Stokes vector Q plus RU you can think of as a particle, and just like the electron has a spin of a half, if Q plus RU was a particle, it would have a spin of 2. And what I mean by this is that if you rotate your coordinate system by 360 degrees, your Stokes vector actually goes around twice. We all know that you only need to go between 0 and 180 degrees to define an angle. In quantum mechanics, that means that this is a spin 2 particle, in the same way that an electron, you actually have to go around twice to get back to where you started. And mathematical functions that have spin have interesting properties. When you take a derivative of a spin 2 function, depending on the exact form of the derivative, you will either raise the spin and create a spin 3 function, or you will lower the spin and create a spin 1 function. So if we want to make a map of the gradient of Q and U, we actually have to pick the right gradient function. Because physically we want a map of the gradient which has spin 1. That is, that it rotates in the same way that the sky rotates. So that tells you what differential operator you have to use. If you want and I should apologise, I'm not a mathematician, so I'm being rather lax in my notation. But if you want some sort of intensity of the gradient, then this is the operator you have to use, partial x minus I, partial y. If this was a plus, then you would actually raise the spin, and you would get a spin 3 function, which would have very strange properties. So this particular mathematical expression, or you can give me any map you want of the sky of Q and U, and I can quite simply compute this quantity. It's quite nice because it's rotationally invariant, it's translationally invariant, and it shows you where the gradient is high. That is, it shows you all possible canals, whether they really do pass through the origin, or if they completely miss the origin, but would be a canal if the translational offset was right. So just to show you what we get, so just to go back again, this is the actual polarized intensity, and you can see the canals. This is our map of angle dispersion, showing you all these different canals going off into the distance. If I now show you a map of the gradient, you can see you get something very different. All the canals have disappeared. There are no structures that are one beam wide. The canals, this is actually a map of the gradient, where this is intense, is showing you where Q and U are changing rapidly, and where it's dark is where they're not changing rapidly. So this is simply now showing you that canals are contours of this particular distribution. What does this mean physically? Well, I'm deliberately going to be a bit vague here. Canals occur whenever the gradient is high, and the gradient is high whenever something about the interstellar medium is changing. So it could be the rotation measure is changing rapidly, as Mareka has discussed. It could be where the amount of depth depolarization is changing rapidly, as Shukarov and Burkhuizen have discussed. It could be where the total intensity is changing, the polarized fraction, or where the angle is changing. But when something is changing rapidly, that's all you need to produce canals. They will simply be contours of that gradient.
Why do you say a spin-1 function is rotationally invariant?
Well, that's probably not the right word to use. What I meant is that it rotates the same way the coordinate axes rotate. So I probably mean the opposite. It's fully rotationally invariant, but it's variant in the right way with a spin of 1. So yeah, I'm using loose language here. So this sort of covers the contour canals that were discussed by Abercorn and by Shukarov and Burkhuizen, but Fletcher and Shukarov suggested there could be a different type of canals which are actually due to a physical discontinuity in the interstellar medium, like a shock. And so the diagram they produced, this is stolen from their paper, is that if you have a shock, then that should actually produce an actual place where the angles abruptly change by 90 degrees. However, if you then add a translation, if you have a place where the angles change by 90 degrees, and then add a translational offset to it, it moves that track far from the origin. And if you move it far enough from the origin, you could still have a discontinuity, but the discontinuity might only be 1 degree. And that would be very hard to see. So again, with the same approach, you can potentially identify shocks in the interstellar medium. So the contour canals I've discussed have a continuous high gradient. There's a high gradient here and here and here. We could move this whole canal, this whole track down to here, and you'd still get a canal. However, what if you had something like this, where the track was actually moving quite slowly, it suddenly sped up, and then it slowed down again? Here you actually have a discontinuity. There is generally a jump in angle here, and it doesn't matter where you translate this track to, you still have the same jump in angle. So, I welcome thoughts on this, but our thought here is that the way you can pick out shocks into the stellar medium is by the third derivative. The third derivative picks out places where the gradient is localized in a very small region. So this is spin 2. You have to lower the spin to 1, you raise it again to 2, and you lower the spin again to 1. And so again, you could potentially compute a map of the third derivative showing you where all the shocks are in the interstellar medium. Unfortunately, in practice, it doesn't work so well because every time you take a derivative, you greatly lower the signal to noise, and for our maps, you just get noise. But in principle, if you have a high signal to noise data set, if you compute the third derivative, it will show you where all these invisible shocks are in the interstellar medium. And the last thing I want to say on this is that there's a nice way you can actually visualize this. Rather than calculate the gradient, why not take the attitude that there's an infinite number of possible translations that you could apply. And if you apply every possible translation and make a movie of all these translations, then you can actually pick out all possible canals of the data. So what we're doing is we start off with our map with polarization as a function of x and y, and we add what we call a spiral offset to it. That is that as a function of a third parameter z, we add a growing amplitude to our original polarization map and a rotating angle. So we're adding an offset, which in the cube plane is a growing spiral. And that way we steadily add every possible translation in all possible directions of data, and we can see canals. What's more, contour canals and shock canals will have different properties. In this, what we call a spiral offset cube, a contour canal will actually shift as you add an offset to it. If you add the right offset, the canal will simply shift to somewhere else along the track. However, a discontinuity canal can only ever occur in one place, so rather than seeing the canal shift, you'll actually see it fill in and fade out again. So you can have a very complicated map full of all different types of canals. Some of them will wobble from side to side as you add this spiral offset, and others will actually appear and then vanish again. So here is the spiral offset cube. Here is our data again, and here's that little heart-shaped canal. Watch the heart, and you will see the heart beating. So you can see, in fact, every single canal on this map is actually apparently a contour canal. Every single canal moves as you add an offset. There are no canals that appear and then disappear. It's quite mesmerizing, but you can see these contours. It looks like a weather map just wrapping across the image as you add different offsets. And I'll just show it one more time. This finishes. So here it is one more time. Just pick some particular point, and you can see the canals do not disappear, but they move. So the conclusion we came to is, at least in this very small patch of the sky, and at this particular frequency, all the canals you see in the interstellar medium are not shocks, but they are all simply contours of high gradients in the interstellar medium. So at least at 1.4 gigahertz, one is being dominated by by high gradient regions rather than shocks. So my time's almost up. I'm going to just quickly jump ahead and talk about some work that my other student, Anne Mao, has been doing on the magnetic field of the Small Magellanic Cloud. We've done a rotation measure survey of the Small Magellanic Cloud. We found 10 sources behind the SMC, and all 10 of them have negative RMs. This little wimpy runt of a galaxy, it's a total mess, has an incredibly coherent magnetic field. Every field line that we can identify is all pointing in the same direction with a strength of about 0.2 microgauss. What's more, when you look at starlight, you also see a very well-organized magnetic field pointing towards the Large Magellanic Cloud. So we have this very puzzling situation, is that we do have a coherent magnetic field in an irregular galaxy, and that's been seen in other galaxies before. Chris has done some work on this, and the Large Magellanic Cloud also. But the real puzzle with the SMC is that we just have one giant flux tube pointing towards us, and no connection. So since the chairman has stood up, it's time to finish up. So just to summarize, we believe that polarization canals are simply a single slice or projection of a much broader set of phenomena hiding in the interstellar medium. And the way that you can get at these is by looking at gradient functions of the polarization vector. Canals are either regions of high gradient or discontinuities which can show up in the third derivative. And the first of those seem to dominate at 1.4 gigahertz. See me later if you want to hear more about the Small Magellanic Cloud, but very puzzlingly, it not only is coherent, but the field is unidirectional, which to my knowledge hasn't been seen in any other galaxy. We're not clear what's going on there, but it may be something to do with the strong tidal modifications due to its interaction with the Milky Way and the Large Magellanic Cloud. And just to talk about some future work, none of anything I said on canals said anything about their frequency dependence. That's a whole other rich source of study, and one can do partial derivatives of partial x, partial nu, or partial x, partial lambda squared to get additional diagnostics that we're starting to look into. We're starting to look at diffuse polarization from the Large Magellanic Cloud to get its three-dimensional structure. And we're also in the process of analysing thousands of rotation measures at the north and south galactic caps to try and measure the parity of the magnetic field in our Milky Way galaxy. Thanks very much.
Thank you very much. Any questions? Oh, Andrew, please.
I almost asked you last night, Brian, what happened to the work that Catherine Newton gave us to us. It's really fantastic to hear about it. One of the things that Anvar and I thought were most useful when we did these calculations was to see, like in your system, the track that you follow in the QU plane. Whether you get like a parabola or just like a diagonal line going through the origin can tell it is sensitive to whether you get the canal is produced by action right along the line of sight, whether you have some kind of Faraday screen. So we're able to identify any difference with these canals, whether they, you know what I mean?
Yes,
whether
yeah,
the track
so,
you follow is different.
Right. So if you translated this particular canal, so this was the origin, then you would have something which changed sign in U but not in Q. Right. Where at this particular point it changes sign in both. So Catherine's actually written two papers on this. One is on what I just showed you, but the other one is basically applying your particular model to the data. And what you find is that tracks are extremely complicated. And what you described is valid if you have a very idealized situation with no turbulence. But it turns out that this curvature or concavity in the track can be produced by a depth depolarization, but it can also be produced by missing spacings, or it can be produced by two RMs beating against each other. So it's actually, there's a lot of different reasons why you can get a curved track. And one thing we are thinking about doing, but I'd love to talk to you guys about, is to actually not make a map of the gradient, but to make a map of the radius of curvature. And where the radius of curvature is smallest might be the places where depth depolarization is strongest. But the equation for radius of curvature, we asked a topologist how you could apply the standard equation for radius of curvature to a complex vector, and they said that was very, very hard. So it's something I'd welcome thoughts on how you could actually compute that.
Could use that E and D decomposition.
We've thought about doing that, but that does some nasty things to you if you don't have short spacings. Like it actually puts flux outside your limits and things like that.
More questions, please.
Right. With this Small Magellanic Cloud, are you confident that it's not the foreground field, some filament in the Milky Way, say?
The short answer to that is yes. What I didn't show, because I skipped the slide, was we have 10 rotation measures through the LMC, but we also have about 60 around it. And these do have a non-zero rotation measure, but you can actually fit to that as a function of right ascension and subtract that out. And the foreground is actually quite small. It's about 20 radians per square meter. These are hundreds of radians per square meter. The Faraday rotation clearly turns on as soon as you hit the edge of the SMC. There's no doubt that this is intrinsically SMC and separate from whatever's in the foreground at that position. See, all these are out here are all.
Are there any signs in H alpha, H1, just any other diagnostic of interstellar medium? Anything special about this galaxy?
About the SMC?
No, not in general about the galaxy, but at least where the field is so strong and not anything else unusual.
No, I mean, this particular point has a very high RM, but it also is coincident, you can't really see it, but it's also coincident with a very high emission measure. So the magnetic field at this position is actually quite normal. The magnetic field across the galaxy, there's actually surprisingly little dispersion, both in direction and in strength. You can see what I said in the next slide. Where is it? There's minus 0.2 plus or minus 0.06. So the coherent component actually is reasonably consistent, but there is quite a large scatter as well.
Last question, please.
Did anybody try to transform the QNU into E modes and B modes like the CNV people do? These are automatically rotationally invariant, so that might help also in the analysis of these features like the canals. So did anybody think about that?
Yeah, we thought about it a lot. But as I was just saying to Kandu, the problem is that they don't have a physical counterpart. So, for example, there's a nice paper. If you go to the original paper by Zaldariaga that proposes these for cosmology, they have an image of a polarized supernova remnant. And the E mode and the B mode, one of them looks like the supernova remnant, but one of them has all this flux way outside the remnant that's completely unphysical. So E and B modes only work well when you image the whole sky. If you're looking at a small patch of the sky, they're not very physical. I definitely want to talk to people who understand this better than I do in the tea break to get some more thoughts. But we did think about that and came to the conclusion that for a small patch of the sky, you're better off sticking with Q and U.
So, thank you indeed. The next speaker is Andrew Fletcher.
F5. F5.
Or just view full screen? Yeah, it's PDF. Okay, so I thought it would be useful for this meeting to try and pull together some work that I've been doing over the last few years with a whole bunch of collaborators here and others. So I've just listed the names of the people that are present at the meeting who've been working with me on this. To try and pull together some, what I think can be useful data that will be relevant to people that are interested in dynamo modelling of disk galaxies. Whether that modelling is in terms of simple back-of-the-envelope style calculations or analytic calculations, or whether they're doing some kind of global numerical simulations or some local numerical simulations to try and pull together some information that could be used, information from the observations that could be used to compare to any type of dynamo ideas. And that's going to be the first part of my talk. It's going to be about this. And basically I'm going to be talking about how we can estimate quantities to do with the geometry or symmetry of the magnetic field that's observed, and in particular the pitch angles of the magnetic field that are observed, which I think are particularly sensitive quantity that's quite easy to measure in the observations, that should also be helpful in calibrating or estimating the usefulness or the accuracy of any simulations or analytic modeling. That'll be about the first half of my talk. And the second half, that'll be about some looking in a bit more detail at what can be the difference between dynamical effects, so where you just have some strong velocity pulling around frozen in magnetic fields in galaxy, and how this can affect what you observe, as against what you might want to attribute to some kind of dynamo action itself. And so that's the second part of my talk. And I'll finish off if I have time, with a couple of things that have proved to be difficult to understand, magnetic arms and the geometry of halo fields. And I have no answers there, but these could be a couple of interesting problems that people might want to address who do dynamo theory. So, on to the first part. I'm going to be thinking about classifying the geometry or the symmetry of the disk fields in terms of Fourier modes. So here's examples of an axially symmetric zero Fourier mode, where the magnetic field lines, so these blue arrows, doesn't matter whether they point in or outwards. And we have an illustration of a M is 1 or bisymmetrical magnetic mode, Fourier mode, or M is 2, where we have the field goes out and then in, and then out and then in, whichever way around it, of course, doesn't matter. And here's an illustration of what I mean by the pitch angle. So if we draw a line, a circumference at a certain radius, and then draw a tangent to that circumference, the pitch angle is the angle that a spiral makes. So it could be a spiral arm of a galaxy or a spiral magnetic field line. It's the angle from the magnetic field line of the spiral arm to that tangent to the local circumference. So that's what I mean by the pitch angle. So to try and get some useful quantities from the observations, some useful simple quantities, what I do is do some modelling. And so it divided the disk of a galaxy up into a bunch of sectors. So I draw a set of rings at fixed radius. So I have a ring at a certain radius here, and a ring at a greater radius here, and then a set of spokes. And this divides up the galaxy into a set of sectors. And the size of these sectors is matched to the level of the resolution of the observational data that we're working with. And then the whole principle behind this is that the large-scale or regular magnetic field in a galaxy gives rise to polarized radio emission. And the angle of polarization that you observe, which I'm calling here this quantity psi, that depends on the angle that the magnetic field makes in the plane of the galaxy. So it's the angle that the emission is emitted at, which is called psi naught, and that depends on one component of the magnetic field. This is the component of the magnetic field in the plane of the sky. And the angle that it's emitted at is rotated due to Faraday rotation on its way to us, and that rotation depends on another component of the magnetic field. That's a field along our line of sight, and some foreground rotation due to the Milky Way galaxy. So we have basically two geometrical components of the magnetic field, something in the plane of the sky and something along the line of sight that affects what we observe. And by making an assumption that the magnetic field is continuous in azimuth, we can then recover by expanding the three different modes, the three different components of the magnetic field in the plane of the galaxy, each into Fourier series. We can recover the three components of the magnetic field, so a radial component, an azimuthal component, and a vertical component, all in terms of just parameters of a Fourier series expansion. And we get these three components through because what we observe depends on a field in the plane of the sky, a field along the line of sight, and an assumption of some azimuthal continuity of the magnetic field. So basically, I try to recover the coefficients of the Fourier series of the three components of the field by making an optimization, by comparing the model with the data and repeating that until I find the best fit. And because this is a nonlinear model, the process is not usually straightforward. There can be several fits, and we need to make some statistical analysis to determine what's a satisfactory fit. So I'm always making a statistical judgment about whether the model that I recover, whether these set of Fourier parameters are acceptable or not, using rather objective statistical measures. So we're using chi-squared measurements and also a comparison of the quality of fits at different frequencies that we're analysing to make sure that we don't have something that's skewed just by a good fit for one set of data and subsequently poor fits for others. So now I'll run through some of the results that I've got over the years. So this is the galaxy M31, it's called the Andromeda Nebula. This is what it looks like on the sky. It's very heavily inclined to our line of sight. If you could see it from one of its poles, it would look like quite a well-defined spiral galaxy, but it's heavily inclined to the line of sight, so it has this elliptical shape on the sky. Here's an example of some of the observation that we're modelling. These little black lines indicate the direction of the magnetic field, the plane of the magnetic field in the sky. And the aim of this modelling is to put the arrows on the end of these lines so that we recover what the magnetic field vectors are. And so by going through this modelling, I recover this description of the magnetic field, which basically all lies in the plane of that galaxy. So there's only radial and azimuthal components of the field. And if I deproject this into the plane of the sky, the magnetic field of the Andromeda galaxy of M31 looks like this. And it's basically a purely axially symmetric M0 magnetic configuration. So then, a different type of, another galaxy M33, this doesn't have such a well-defined spiral pattern. This is what it looks like on the sky. This is what some of the observations look like. Again, the objective is to put the arrows of the magnetic field onto the orientations of these black lines here, the polarization vectors in the sky. Again, by going through the modelling, I end up with a field configuration in the plane of the galaxy that's a simple M0 axisymmetric mode in the innermost ring that I have here, and there's a combination of M0 plus a bisymmetric mode in the outermost ring. To get a good fit to this data, though, it turned out to be necessary to have a vertical component of the field in both of these rings as well. And this is the only case where I've come across where we need to have some large-scale vertical component of the magnetic field. I think this probably arises because of a strong warp in the plane of this galaxy. And so this region in the lower part is kind of bent up towards us, and this region, the opposite region in the upper part of the galaxy, is kind of bent away from us. And I think this warp in the plane of the galaxy is giving rise to this modelled vertical components of the field here and here. I think that rather than seeing something that's really sticking out of the plane of the galaxy, it's the fact that we need a vertical component of the field to model this because of bending of the plane of the galaxy. Yeah, sure.
What? Will there be a signature in radial velocity?
Yes, and that's where the idea of the warp comes from. The idea that that galaxy's warp comes from the velocity field observed in neutral hydrogen emission. So, another case, the galaxy M51 is a very strongly has a very strong two-arm spiral pattern. This is the galaxy that Anvar Shukurov showed at the beginning of the discussion last night to show that this is a map of the Faraday rotation. So we're using that as one of our measurements of the components of the magnetic field, this component of the magnetic field along the line of sight. And Anvar was saying that this information here looks very chaotic. It doesn't look very highly ordered. And what is the right way? What needs to be done? Or is there any ordering here? And what needs to be done to recover that ordering? And through this modelling process, we can find that underlying this rather chaotic-looking structure in Faraday rotation, we have quite a simple structure of regular magnetic field. It can be modelled by just a combination, a superposition of axially symmetric M0 plus a doubly periodic MS2 mode. To find that, as well as making this averaging in sectors by dividing up the galaxy into this whole set of sectors, we needed to carry out a Fourier filtering of all of the data, all of the radio data that we had, to extract only large-scale structure in the observations. Once we had extracted that large-scale structure and divided up that large-scale structure into these sectors, we recovered quite a simple model of the regular magnetic field. So filtering was necessary here. And in the end, it's not so surprising, because when we look at the raw data at one frequency, you see these little yellow lines are indicating what the orientation of the magnetic field in that galaxy is. And it looks very well ordered. It looks like it has a pitch angle. It follows the spiral pattern of the optically visible spiral arms over huge distances from the inner part of the galaxy right over to the outer part. And it would be very surprising in this case if there wasn't something large-scale underlying that pattern seen so clearly just by looking at the observations here. Of course, we don't know where the arrows are, so one idea was that these arrows could all be pointing in different directions, and we had something that was quite anisotropic, all being packed together for some reason. So magnetic field that was pointing in different directions, say out and in here, was just all being compressed together to produce this spiral pattern of the field. But with the right type of filtering and modelling,
we find quite a simple structure of the regular magnetic field here, with the axially symmetric mode being stronger than this 2 mode is basically a perturbation of it.
There must be a random field also.
There's a random field also. I'm not
Which will become-
discussing anything about the random field yet, but there's a random field that does contribute to these fluctuations in Faraday rotation that you see there.
Do you model it or do you subtract it, or what do you?
There was a filtering, so that filtering subtracted lots of, that filtering that I talked about took away lots of small-scale structure in this map before I went to analyse it. And then it's averaged as well into these kind of chunks.
But this there's other fraction is also interesting on its own right.
Yeah. I'm just concentrating now on what we find from the regular magnetic field. So to go into discuss two other cases. These last 2 cases are barred galaxies, and it's worth showing these because these galaxies have a very strongly their velocity field is highly non-circular. So for normal spiral galaxies, you have a velocity that's basically circular. So the gas just orbits the centre of the galaxy in roughly circular orbits, but its speed, the velocity of these orbits is roughly constant once you get beyond a certain radius, and that produces lots of shear. But in these barred galaxies, the gas follows a kind of a circular trajectory away from the barred region here. Once it reaches this barred region, its velocity shifts and it basically follows orbits that go around the centre of the galaxy like this. So the gas comes into the bar, it's diverted towards the centre. When it leaves this bar region, it moves out again, goes around here again, comes into the bar, is diverted towards the centre, leaves the bar, comes out in this sort of trajectory, goes in and out and in and out as you go around. So it's highly non-circular velocity field. If you do the same type of modelling with the same type of data, we end up with magnetic field structures that still include this axially symmetric mode. And not surprisingly, we end up with other higher modes of the Fourier series that are required to describe the field. This field all lies in the disk still, there's no vertical component. But what's surprising now, I think, is that you have such a distorted velocity field, such a non-circular velocity field, but this axially symmetric mode in the regular magnetic field structure still starts showing up. And that occurs in this galaxy, NGC 1097, and similarly in another barred galaxy, NGC 1365. So to describe from the observations the magnetic field structure, we still find that we need to have this axially symmetric mode, even though the velocity field is highly non-circular.